Good morning. Today I will be covering the last chapter on this earthing grid design. So in the first chapter I told about the introduction. In the next chapter I told about how to determine the step and touch voltage, tolerable values. And in the next chapter I have told about how to determine the step touch voltage, that is the mesh voltage and the touch voltage which can be attained in a substation. And I have also taken one example. Now in this chapter I am covering that example. Case 1 has already been covered. Now I am going to case 2. Case 1 was the ideal case where I took a 40 kA fault current and we found that the touch and step voltage, that is the mesh voltage and the step voltage which were attained in a substation, was much high than the tolerable value. Now I will take this case 2. Case 2 is a realistic case and I will explain with an example on how to design an earthing grid for a substation based on this realistic case. Please note, the reason why I am already writing this before is to cut short the time. That is one thing. I don't want to waste my time writing a lot. And second thing which I want to stress again, please do not try to memorize any formulas. It will be of no use. Just understand the steps, understand the meaning of each and every notation, and also you should know what are the units, whether it is in meter or feet or kilometer, is it in amps or kiloamps. And also you should know, you should have a fair idea about the values. For example, the step voltage may be, let's say, the mesh voltage which is attained may be 2000 volts or 3000 volts, something like that. It may not be something like 20,000 volts. So you should have a fair idea about the values which can come. And the grid resistance may be, let's say, 0.5 ohms or 1 ohms, and the division factor may be 0.3, 0.4, 0.5. So basically you should have a fair idea about the values that we can expect. So remember 3 things. Don't try to memorize any formula. Just know the steps and the notation. Number 2, you should know the units. Number 3, you should have a fair idea about the final results. So coming back to the case example, now this is a 220 bar 66 kV substation. We have a 220 kV 2 main bus and a 66 kV 2 main bus. And this 220 kV bus is fed by 6 transmission lines. Basically it is 3 double circuit transmission lines. And we have a provision for expansion. We can add 2 more bays, that is 4 more transmission lines. Now these are the 6 transmission lines. Now let's say there is a fault inside the substation, that is on the bus or in the line within the substation. So you should know that the substation is protected by bus bar differential relay. There are different types of protection: transmission line protection, transformer protection, bus bar differential protection. So for any fault on the bus in a substation, the bus bar differential relay acts, and this differential relay acts instantaneously. When we say instantaneously, there is no intentional delay, but there is some small delay due to the time taken by relays or CT, etc. For calculation purpose, we will take this as 100 millisecond. In reality, it will be much less than this. When there is a fault here, we have to determine what is the fault current. In order to determine the fault current, we have to do the short circuit calculation. That is a separate chapter. I will explain about it some other time. We have found out that the contribution by each line was 3.5 kA. So there are 6 lines, so it will be around 21 kA. And considering two future lines, if we consider 2 future lines, the future line will contribute around 7 kA. So totally we get this 28 kA as the fault level. So previously in the design case it was 40 kA. Now the fault level to be considered is 20 kA. Later on I will show in the calculation this grid current will not be 20 kA, it will be much less than this. So the fault current is 28 kA and the operation time is 100 milliseconds. See, previously it was 1 second. So now this 1 second has become 100 milliseconds. Previously, in previous case it was 40 kA. 40 kA became 28 kA. Now the step voltage is given by this formula, which you have already seen in the previous example, 0.116 by root T. T is 100 millisecond, that is 0.1 into 1000 plus 6 rho. 6 rho S, CS. Rho S is the resistivity of the surface material, which is the resistivity of the gravel, which is 2000 ohm meter. And CS factor was already calculated in the previous example, it was 0.72. So we get the step voltage as 3536 volts. Similarly, let us determine the touch voltage, which is 0.116 by root T, which is into 1000 plus 1.5 into 2000 into 0.72, we get it as 1160. Please observe one thing here. In the previous case, when we considered 40 kA for 1 second, the step voltage which was attained in a substation was, I think, the step voltage was much higher. The actual value, step voltage, let me just check once. In the previous case, it was around 649 volts was the this is not the voltage which is attained. This is the voltage which can be tolerated. In the previous case, the voltage which can be tolerated was around 366 volts. Previously the voltage which could be tolerated was 366 volts. That is, any voltage above 366 volts would be fatal. But now that voltage has increased. Sorry, I think there is a mistake here. Three 1119. Okay, now it is clear. How could I make out this mistake? Is very simple. Normally the touch voltage is smaller, the step voltage is higher. So as I told you previously, have a fair idea about values, because sometime when we are doing calculation we are bound to get confused. So since I had a fair idea that touch voltage will be smaller, step voltage will be higher, I could trace out the mistake. So now, in the previous example, when the design case was 40 kA for 1 second, the touch voltage was 366 volts. The same thing now got increased to 1160 volts. Similarly, the step voltage was 1119 volts. The design when we consider 40 kA for 1 second, the same thing now got increased to 3536 volts. So you can see almost around 3 times the voltage has increased. What is the advantage of this increase in voltage? What does this mean? Basically, when you touch something or when you step on something, there is a voltage which causes a shock in our body. So we are allowing a higher value for that. So till a person does not come in contact with 1166 volts, there is no fatality. So the person is safe. So whenever the tolerable value of step and touch voltage increases, the safety increases. So that is the advantage of reducing the time. One more thing I want to tell: this step and touch voltage has nothing to do with this current. It is influenced only by the time, whereas this current influences the actual value. The tolerable voltage is influenced by the time. Please note, tolerable voltage is influenced by the time. The attained voltage is influenced by the current. So please note this difference. So these first two voltages are the tolerable values, the one which below which there is no fatality. This is influenced by the time. Now the subsequent one is the attained voltage, the voltage which actually happens in a substation, the actual value. These are influenced by the current. Now, the mesh voltage, as I have already explained in the previous example, mesh voltage is the voltage at the center of the corner mesh. Now, this is the maximum touch voltage which actually takes place or happens in a substation. This is given by the equation rho Km Ki Ig by Lm. So rho resistivity is 200 ohm meter. The constants Km is 0.17, Ki is 7.72. As per the previous example, it's already calculated. Lm is the total length of the grid conductor, horizontal. It is around 13,800 meters. And Ig is the grid current. Ig is not 28 kA, because when there is a fault, what happens? See, if the fault takes place 28 kA here, see, the fault has to return back to its source. So all the fault current returns back to its source, but in a different path. One goes through the earth grid, through the earth. The other one goes through the neutral wire of the transmission line. Sorry, not the neutral, the earth wire. There's a difference between neutral and earth wire. The earth wire is the wire which goes on the top of the transmission line. It is for the safety grounding. So the 28 kiloamps gets split into two parts. One current goes through the earth wire of the transmission line. The another part goes through the earth. The one which goes through the earth, it is this current which causes the ground potential rise. So we are concerned about that part of 28 kA which flows through the earth. So we have to find out that percentage. That's why we have this factor SF. So what is this factor SF? It is given by equation Z equivalent divided by Z equivalent plus RG. This is nothing but current distribution. When we have a current going through two different resistors, the current in the branch A is nothing but the resistance of branch B divided by the sum of resistance of branch A and B. So that is simple circuit theory. So this Z equivalent is nothing but equivalent to Zs by 2 plus square root of Zs plus Rt. How we got this equation is basically our transmission line is taken as a distributed parameter. So with every span, one distributed parameter. So when we combine all those distributed parameter network to a lumped network, we get this equation. Zs by 2 plus square root of Zs into RT. RT is the tower footing resistance. At every tower of the transmission line, we do some earthing. So the resistance of that footing is RT, and it is normally around 10 ohms. So, but please check about this for specific values. Now Zs, what is this Zs? This Zs is nothing but, I have already explained in the chapter 2 about Zs. Basically when the fault current flows, see the fault current flows in something like, see if this is the line, the fault current flows through the phase conductors. It's a zero sequence current and flows into the fault path and finally goes back through the earth wire. So there are 3 phase conductors and 1 earth wire. So this phase conductor resistance is given by this particular value. So it is Re plus Jxe divided by 3, and this earth wire is equal to Ra plus Jxa. This is the so when we add these two quantities, we get this Zs. So Ra is AC resistance of the earth wire, and Xa is the self-impedance of the earth wire. So this first term corresponds to the earth wire. The second term, Re, is the resistance of the phase conductor, and Xe is the self-impedance of the phase conductor. So Ra is given by this formula. Sorry, there is no formula for Ra. You have to determine, you have to check some of the catalogs to get Ra. Here the earth wire used, what is the earth wire? Normally earth wire will be a galvanized iron wire. So here we have used 7-strand galvanized iron or galvanized steel wire, 7 bar 3.5, that is 7 strands and each strand of 3.15 mm. So for that Ra was around 3.4 ohms per kilometer. So we got Ra. Next is Xa. So where is Xa? Okay, Xa, there is a formula for Xa. Actually this formula is a very old formula. It is given in T&D handbook, and later the same thing is referred in IEEE 80 also. Whereas this equation is from a IEEE paper. Please see the guideline for more details, and also guideline is for the IEEE 80. You need to refer the IEEE 80 also. Okay, coming back to this formula on Xa. Xa is given by 0.06327 log 1 by GMR into 0.00328. So this is the formula for Xa. GMR is geometric mean radius. How do we get this GMR? There is a formula for that. I will not explain now. So we got it as 0.00348. So finally Xa was determined to be 0.72 ohms per kilometer. Ra is 3.4, Xa is 0.72 ohms. So normally X is more than X by R, but for ground wire R is more, X is small. Then Re and Xe. Re and Xe corresponds to the phase conductors. Re, this the value for Re is 0.149 ohms per kilometer for any conductor. Coming to Xe, Xe is given by this formula, 0.0949 natural log. This is natural log, not log to base 10. 93310 rho. So when we substitute, we got it as 1.588 ohms per kilometer. Here you can see X is more than R. So we got RA, we got XA, we got RE, we got XE, we substitute, we get ZS. ZS, we got it as 3.659 ohms per kilometer. This is the value of ZS for one line. Now, in this equation, ZS is nothing but ohms per span, not ohms per kilometer. What do we mean by span? We have two transmission line towers. The distance between them, one span is between two towers. So in our example, we have considered the span as 320 meters. This can vary from example to example, case to case. So you need to know the actual span. In our case, it is 320 meters. So we got ZS per span is nothing but 3.659 into 0.32, that is 1.17 ohms per span. Now we need to find the Z equivalent. Let us substitute ZS per span, 1.17 divided by 2 plus square root of 1.17 into 10 ohms, which is the tower footing resistance RT. We get it as approximately 4 ohms. This is for one line. So we have 8 lines. 8 lines is because we have 6 lines at present and 2 future lines. So we need to consider future also, because we cannot again change the earthing grid design in future. So we need to consider all the fault contribution in future also. So for 8 lines, we get Z equivalent as 0.5008. So this factor SF, we got it as 0.5008 by 0.5008 plus 0.47. See, what is SF? Z equivalent. Z equivalent is 0.5, which we have found out here, plus RG, the grid resistance, 0.47. I will explain how we got the grid resistance. See why basically the earth fault is dividing into two different paths. One is, it is whenever there is a fault, the fault current is flowing through the earth grid, and the another part of the fault current is flowing through the earth wire of the transmission line. So these are the paths in which the fault current flows. The 28 kV fault current undergoes two divisions. One is through the earth grid, which has a resistance of Rg, and another one through the transmission line earth wire, and so which has Zs as the impedance, earth wire as well as the zero sequence network. So that's why we have to take this division factor as it is not Zs, it is Z equivalent. Z equivalent divided by Z equivalent plus Rg. So when we take this, we get this as 0.512. What does this mean? This means 51% of the fault current, 51% of the fault current flows through this. Out of 28 kA, 51% of the fault current flows through the earth grid, through the earth. So it is around 40 kA. Now let me explain how we determine the grid resistance. This is very simple. There is a formula given in IEEE 80. I am just using that. Rg is R1 R2 minus Rm square by R1 plus R2 by 2Rm. What does this mean? The earth grid resistance, see, this basically indicates it is parallel of two resistors. One is the resistor due to the horizontal conductors. One is the resistor, that is R1. The another one is the resistor due to the vertical ground rods R2. And this is the mutual resistance between R1 and R2. So R1 is given by this formula, rho by LC pi into log 2 LC by A dash plus K1 LC by root A minus K2. So there is an equation. So this K2 and K1 are constants. So there is a figure given in IEEE 80 to determine these constants. So you can look at them. A dash is given by root of A plus 2H. What is A? 2A. Basically the conductor has a diameter, the horizontal conductor. 2A represents the diameter of the horizontal conductor. And H, you know, is the depth of burial. In the previous case, for diameter we were using the term small d, whereas here they have used a dash and 2a. I'm just following as per IEEE. So we substitute the values and we get R1 as 4.5. Rho you know is 2000 ohm meter. LC, the length of the conductor, is 13,800 meters. And area A is nothing but length into breadth of the earthing grid. Length was around 160 meters, breadth was around 130 meters. So we got it as 20,800 meters. So we got, what is the final value of R1? We got it as 0.47 ohms. Similarly, let us find out R2, which has the equation rho by LR 2 pi NR log 4 LR by B minus 1 plus 2 K1 LR by root A into square root of NR minus 1 whole square. So this equation is already there. Again, don't try to by heart it. Rho is the resistivity, LR is the total length of the vertical ground rods. Total length of the vertical ground rod is nothing but, if we have 500 ground rods, each of 3 meters, so it is 500 into 3, 1500. NR is the, that's why LR into NR is equal to 1500. And LR, B, okay, B is just like EA, 2A here we have B. B is the radius of the conductor. Let's assume that the vertical earth rod is 30 mm dia. So the radius becomes 15 mm, and this is in meters. The units is in meters. That's why we are writing as 0.015 minus 1 plus constant K1 LR by root A, area about 20,800 into NR, number of ground rods, root 500 minus 1 whole square. So finally we get R2 as 0.5235 ohms. So R1 is the resistance of the horizontal grid is 0.47 ohms. R2, the resistance of the vertical ground rod, is 0.523 ohms. And Rn, the mutual resistance between these two, is found out by rho pi LC into log 2 LC by LR plus K1 LC by root A minus K2 plus 1. And we substitute all the values, we get it as 0.467 ohms. So finally we find out the grid resistance Rg, which is nothing but parallel of R1 and R2, and we need to remove the mutual effect, and that gives us 0.476 ohms, and that is 0.476 ohms. So when we substitute this grid resistor in this equation, we get the fault current division factor. So Z equivalent was what was Z equivalent? Z equivalent is 0.5 and Rg is 0.47. So we got SF as 0.512. So the fault current. So now let me write about one more factor. Okay, I will write the SF is 0.512. We have the grid, the fault current was 28 kA. The grid current is nothing but SF into 28 kA into DF. This SF is the factor, the division factor, which takes into account the current which flows into the grid. Since 50% of the current is flowing to the grid and the rest through the earth wire, we need to consider only 50% of 28 kA. And this factor DF takes into account the asymmetrical current. So whenever there is a fault, if the fault is symmetrical, it is like this. If the fault is unsymmetrical, there is a DC offset. Now because of this, basically this current added to this current, this is the DC. this current added to this current gives the asymmetrical current. And because of this asymmetrical current, what happens is the value of the RMS equivalent increases. So we find out, we take this factor df. This factor df is again given by a equation. This decrement factor is given by this equation. df is equal to 1 plus 1 plus 1 plus dA by 1 plus dA by df into 1 minus e to the power of minus 2 df by dA minus 2 df by dA square root. So this dA is nothing but the time constant. df, so this df is the fault duration. Okay, df is the duration of the fault. In our case it is 100 millisecond. dA is the DC time constant. The DC time constant depends on the x by r ratio. It is given by dA is equal to x by omega r. And in the previous calculation I have already shown the x by r. This is x by r of what? X by r of the, not the earth wire, this is the x by r of the transmission line. See, previously we got the value of R and X of the earth wire. We got the value of R and X of the phase conductors for a zero sequence current. But this X by R is the R and X value of the phase conductors for the positive sequence. So this X by R, please check the transmission line constants. So I have not done the calculation here. So we get it as around point, okay, 5.7. So I have referred one 220 kV line typical values, and I got the x by r as 5.71. So as I told, please refer some manual for the x by r of the 220 kV line. I got it as 5.71. So x by r divided by omega, I got it as 0.0187. So with this, I got the DC time constant. So that is, if I write this in seconds, it will be 180.1 is 100 millisecond. It is 18 milliseconds with the DC time constants. So when I substitute TA as 0.187 and TF as 100 millisecond, so we got the value of DF as 1.0894. I will write it as 1.1. In other words, this fault current, which was 28 kA into 0.5. Fault current was 28, it is 28 into 0.5 becomes 14 kA. In order to take into account the DC component, I need to increase it by another 10%. It will be around 15.4 kA. So now, when I substitute these values, so now I come back to this equation. the mesh voltage. The mesh voltage is nothing but 200 into 0.17 into 0.772 divided by 13866 into 15400. 200 into 0.515 into 7.72 divided by 1164 into 5400 1048. So this current is around 15,680 amps. 15,000, the correct value for that is out of 28 kA, around 14 kiloamps of current flows through the arc current. So taking the factor for asymmetrical current into account, we get the current as 15,680 amps. Now this current needs to be substituted in this equation for mesh and step voltage. So when we substitute this, we get it as 27.72 divided by 11674 into 15680 106. So this is around 1068 volts. So the step voltage, which is, so I substitute for this grid current. I get the step voltage as 1068 volts. Yeah, step voltage. So you can see the step voltage. So you can see, I will just use one more pen. The step voltage attained is 1068 volts. It is much less than the tolerable value, which is 3536 volts. The step voltage attained, which we have calculated, is 1068 volts. It is much less than the step voltage, which is tolerable, that is 3500 volts. So our design is okay from step voltage point of view. Similarly, let us determine the mesh voltage. Is 200 into 0.17 into 7.72 divided by 13866 into 15680, that is 296 volts. 296 volts. So 200 into 0.17 into 7.72 divided by 13866 into 15680. I got this as 296 volts. So the mesh voltage is 296 volts. So this is below 1119 volts. The mesh voltage attained is below the touch voltage tolerable, 1000 volts. So step attained 1000 volts is below step tolerable 3500 volts. Mesh voltage attained 296 volts is below touch voltage tolerable 1100 volts, so our design is okay. So with this I complete the example 2. There are 2 more examples in the guide. I will take them. I'll take them later. So this is about case 2. Basically what I did was I took a case of a fault on a 220 kV bus in a substation, and the substation is protected by a differential relay. So the time for operation was assumed as 100 millisecond. The fault current was calculated from short circuit studies as 28 kA. Then I determined the fault current division factor, which is based on the current distribution based on circuit theory. So I found out Z equivalent and Rg. For Z equivalent there is an equation. In order to get that Z equivalent I need to know Zs and Rt. Rt was 10 ohms and Zs, there was an equation for Zs, and for that I need to know some transmission line constants, and there were some equations for that, and finally I got SFS 0.512, and then I had to find out the equivalent value of asymmetrical current, RMS equivalent of asymmetrical current. For that I need to know the DC at the time constant x by r. From that I got df as 1.089. From this df and sf, finally I found out the fault current equivalent as 15,680 amps. I substituted them back in these 2 equations, and from them I got the touch and the step voltage which are attained, and I found out that the step voltage attained was 1000 volts, and the touch voltage attained, which we call as mesh voltage, was 296 volts, and they were below the tolerable value. That's it about this case 2. Thank you.